In this video, we're going to look at this problem, which is like a problem we've solved before. We have two masses. One is sitting on a surface. We're going to let it be frictionless, and then we're going to give it some friction. And then we have one hanging from a string that passes over a pulley. Now, when we've done this before, we've had massless strings and massless frictionless pulleys. We're still going to have massless strings, but now we have a pulley that has a mass of 5 kilograms and a radius of 5 centimeters. So, because this pulley now has mass, we're going to have to take that into account when we let our system, after we let these go, when we let our system evolve. Specifically, one of the things we cannot do, I've given it to you in the hint here, is assume that the tensions in these cords are equal. That is the case if we have a massless, frictionless pulley, but we don't have that anymore. It's frictionless, but it's not massless. We cannot assume that. So I'm going to have different tensions for either of these things. For both of these strings. So first things first, let's do a little background work. I've given the three masses here. Mass of the pulley is 5 kilograms. I've just called this mass 1. Mass 2, 15 and 25. I'm going to do the same trick I almost always do, which is to express the masses in terms of the other masses. So in this case, it's mathematically easy. Let's take the 5 kilograms as our base unit. So we're going to let the pulley be mass M. We're going to let this be mass 3M, and we'll let this be mass 5M. It doesn't always work out so prettily, but in this case it does. So I like this much better than trying to deal with M1, M2, MP. Again, you don't have to take this step. You can leave them in subscripts if you want to, but I think this is cleaner. We have a radius of the pulley, 5 centimeters. Let's go ahead and make that 0.05 meters because we'll need meters. Now, I'm also going to need, because this is a pulley that has a mass, I'll need the moment of inertia of the pulley. I'm going to let that be modeled as a disk. I look up the moment of inertia of a disk, and I get that I disk is equal to 1/2 mr squared. I've got all that information, so I now know the moment of inertia of the pulley. All right, so let's think this through. This is a coupled system. So what I know is that any displacement of this mass will have a corresponding displacement of this mass. Any velocity of this mass will have a corresponding displacement of this mass. Velocity of this mass. And the same for accelerations. And that's what I'm going to use to couple this system. Now, I've got to think about what's happening here in the pulley. Because if I have this mass accelerating downward, then this is obviously accelerating to the right. But what's the pulley doing? Well, the pulley then is rotating and accelerating clockwise, this way, right? If this mass moves down, that means the pulley goes clockwise, and this mass moves to the right. Now, it's easy to see that I can couple up the accelerations of these two, but what about the pulley? The pulley has no linear acceleration, or at least, the pulley's not moving linearly. But it does have an angular acceleration. And if I have an angular acceleration of something in a circle, and I know the radius, I can always turn that angular acceleration into the linear acceleration of a point on the rim. That's the tangential acceleration. Remember this equation. A tangential is equal to R alpha. So if I can determine alpha of this, I can find the acceleration of this point. That is the point where the string is in contact with the pulley. Now think about that. If the string is not slipping on the pulley, right? If the string if the pulley's rotating and the string is not slipping, the acceleration of this point on the rim of the pulley has to be the same acceleration as the rope. But the rope has to be the same acceleration as this mass, and also this mass. So that's what I can use to couple them. Let me say that again. If I can find the tangential acceleration of this point on the rim, right? I find the angular acceleration of the pulley, that gives me the tangential acceleration of this point. that acceleration of this point has to be the same as the rope. The acceleration of the rope has to be the same as the acceleration of this mass. That's what I can use to couple them. So I've got this for the pulley, which means, of course, that alpha is equal to A. I'll leave off the tangential because that's what it is here. And we know that, over R. So I might need these as I'm solving this. This is all still just background work. Now, let's do it. Part A, draw free body diagrams of all three objects. Well, we'll do this one first. I've got 3mg, right? It's just mg, but I'm using 3m. And then there's this normal force. And then I've got the string, which is pulling it this way. I'm going to call this T1. Again, I can't let the tensions be the same. I'll call this T1. And because I've read through the problem, part B says if the table is frictionless, part C says, well, now let's add some friction. So why don't I just go ahead and sketch in, I'll do it as a dotted line, the static friction here, because I'm asking about static friction in part C. So I'm just going to sketch this in with the understanding that we won't need this for part B because it's frictionless, but we will need it for part C because it's not frictionless. All right, that's the free body diagram of this one. Let's do this one. This is 5m. And then I've got T2, again, different tension. That's two objects. Let me do the pulley. There's my object. Okay, so what's touching it? Well, first, yeah, I've got gravity. That's mg. And then I've got whatever's touching it. So I've got several things touching it. This rope is touching it. That is T2. I called that T2 here. This rope is touching it. That's T1. And assuming it's a pulley, it has a pin. I've also got some sort of support force from the hinge or the pin. So this is the free body diagram of the pulley, and it looks pretty complicated. But notice the support force and gravity are both applied at the center. And because this is going to be rotating about the center, that's the point about which I'm going to sum the torques. And remember, no force produces a torque about its own point of application. So when I sum the torques, gravity and the support force won't contribute. Only the tensions will contribute. Now, I need positive directions. I'm still going to couple up everything so that a positive motion of this mass means a positive motion of this mass means a positive rotation of the pulley. So let's do this. There are my positive directions for mass 1. Here are my positive directions for mass 2. And that corresponds to a clockwise rotation of the pulley, so I'll call clockwise positive. I know that goes against the convention, but I don't care. This is going to work for us. Okay, so let's continue on. This is part A. That's free body diagrams. What about part B? If the table is frictionless, so we're ignoring this, determine the acceleration of both masses. That would be these two. Well, again, I'm going to couple these up by looking at the angular acceleration of the pulley. So let's write Newton's law for all three of these. For this mass, I'm going to get, or just reading off the free body diagram. In the x direction, I don't think I need to worry about the y direction just yet. But you know what? We'll do it because we'll need it for part C. Sum of the forces in the y direction is equal to ma sub y. We don't expect this to come off the table or go into the table, so that's 0. And so what I get is normal minus 3mg is equal to 0, so normal is equal to 3mg. Fair enough. Now let's look at the sum of the forces in the x direction. I'll just do it down here. I've only got T1, but that's ma. I'm just going to call this m. Well, we'll call it a sub x. That's fine. No, I'm sorry. Let's get rid of that because this is the only real acceleration that I have. This just goes to 0. So let's just call it ma to get rid of the subscript. If you want to call it ax, that's fine. I'm just going to call it ma. If this is frictionless, I know it's going to accelerate. So when I unpack this, I get T1 is equal to that's 3m A, right? This is 3m. So 3m A. All right. Now, let's do Newton's second law here. I don't think I need the y direction. There's nothing happening. Remember, y is horizontal here. X is vertical. So sum of the forces in the x direction is equal to ma. Looks like I've got 5mg minus t2, because down is positive, is equal to, what's this? 5ma. And that's all I have on this one. Let's do the sum of the torques now on this one. Again, I'm summing it about the center so that the support force and gravity don't contribute. So I can say sum of the torques is equal to I alpha. Okay, so I know what I is. And we've already seen that to couple these, look, here's where this comes into play. I'm going to write alpha as the tangential acceleration over r, just from this expression, recognizing that the tangential acceleration of this point has to be the acceleration of the rope, has to be the acceleration of this thing. They all have to match up because it's coupled. So what do I have here? Well, I have two forces. I've got T2 and T1. Notice T2, if T2 wins, that's going to make this thing rotate positive. So the torque produced by T2, I'm going to call positive. So T2, I will put in the distance in just a second. T1 is going to cause a negative rotation, so I'll say minus T1. That's only part of it. Of course, those are just the forces. To make them torques, I need to multiply them by the moment arm, or the straight line distance, the perpendicular distance, I should say, between the point of application of the force and the point of summation. That's just the radius of this thing, right? The T1 and T2 are being applied at the rim. It's rotating about the radius, or it's rotating about the center, so it's the distance between those is just the radius. So I'm going to get, for both of them, T2 times R, and that's minus T1 times R. And that's the left side, equals, well, what's my moment of inertia? 1/2, and this is just m and r squared, times alpha. This is the moment of inertia, times alpha. But I'm going to write alpha in terms of the linear acceleration of the rim. So that's A over R. Now, let's clean this up a little bit. I've got an R squared here and an R here, so I lose that and that. I've got an R now in every term, so I can lose the rest of the R's. And I'm left with T2 minus T1 is equal to 1/2 ma. Now I'm getting somewhere, okay? So I have these three equations. This one in terms of T1, this one in terms of T2, this one in terms of T1 and T2. So it looks to me like if I'm going to eliminate some things, maybe a good strategy would be to solve this one for T2. This is already solved for T1. If I do that, I'm going to get T2 is equal to 5m, and I'll factor it out. That's going to be g minus a. Yep, that's right. And now I have this for T1, this for T2, and this for T1 and T2. So this tells me what T2 minus T1 is. Well, why don't I do that here? T2 minus T1 here, from these expressions, gives me 5m g minus a, that's T2, minus T1 minus 3m a is equal to 1/2 m a. Now I'm doing good, because look, I've got an m in every term. I can get rid of that. I'll need to distribute this, right? That's going to give me 5g minus 5a minus 3a is equal to 1/2 a. Well, let me collect like terms. I'm going to move all my a's over. I'm going to have 5g is equal to 1/2 a plus 3A plus 5A. I get 8.5A here. So 5G is equal to, we'll say 17 over 2A. That's 8.5. So therefore, A is equal to, if I multiply both sides by 2/17, I'm going to get 10 over 17G. How did I get that again? Let's go through that process again. I did free body diagrams. I recognized that what couples these systems is the acceleration of a point on the rim of the disc, which has to match the acceleration of the rope that is applying that torque. That rope is connected to this mass, which means that's the acceleration of this mass. It's also connected to this mass, which means the acceleration of that mass is the same. And then after that, I solved all of these for the tensions, because if I'm looking for the acceleration, what I need to get rid of is the tensions. I have two tensions here, which means I need another equation to eliminate it. I got it from the torque, and I then just used these equations to eliminate T1 and T2. I was able to do it in one fell swoop because this is nice and simple, and that gives me A right here. So, reasonably complicated problem, but once you learn how to do it, once you learn how to couple it, it's not terrible. Now, of course, we're not done. We've got part C, but, so now if the table is, should be table, not tables. If the table is not frictionless, determine the coefficient of static friction necessary to keep the system in equilibrium just before it slips. Just before it slips is code word for maximize the static friction, right? That means we can say static friction is equal to mu static normal. I solved for the normal force here. So for part C, I'm going to rewrite all these equations, but now I'm in equilibrium. So everything is 0. Some of the forces, I don't think I need to do the y. I've already done it. Let's just do the x. It's equal to ma sub x, but that's 0. So I get T1 is equal to 0. No, sorry, that was not going to work. T1 minus static friction is equal to 0. I was wondering how that was going to work out. Yeah, because I have static friction now. Let me go ahead and put in what I know static friction to be. If it's maximized, that's mu static normal. So that's T1 minus mu static. Now, what's the normal force? Well, it's right here. Mu static times 3mg. And that's equal to 0, so let me just move that over and say that T1 is equal to mu static 3mg. All right, so I could solve for mu static from here. That's what I'm looking for, but I don't know what T1 is, right? So we have to slow down on that one. Let's look at Newton's second law here. Sum of the forces in the x is equal to ma sub x. That's still 0. What do I have in the x direction for this? Well, I still have 5mg minus T2. But that is equal to 0, so that means T2 is equal to 5mg. All right. Now, if I look at the pulley, I can now say the sum of the torques is equal to I alpha, but alpha 0 because I'm in equilibrium. Right? I should make sure this is a different problem here, or a different section. Now, when I sum up the torques, I'm still going to sum it about the center. So support force and gravity still not contributing. What does contribute are T1 and T2, and what I'm going to get is T1 times the radius. It's still the distance between the point of summation and the point of application. I did it backward. I did it the other way up here, so let me do that. T2 times the radius minus T1 times the radius is equal to 0. All right, so let's get rid of the radii. That's going to give me T2 is equal to T1. That's handy, because what that means is I can now take T2, which is 5mg, and set it equal to T1, which is mu static 3mg. 5 mg is equal to mu static times 3 mg. This tells me I can do that. Now I've got an mg in both terms. So it looks like mu static is equal to 5 over 3.